Okay, this is section 3.22, and we're, I think, finishing, section 3.2, and we're finishing up, I believe, with 3.22, Theorem 3.22. And here it says if A is row equivalent to B, then the row space of A is actually the same subspace as the row space of B. Okay, and the proof, we're just going to use our theorem 3.2.1 to get this theorem 3.2.2, and so if A is row equivalent to B, what that means is I took a bunch of elementary row matrices and multiplied those by A to get B. Okay, how many? I don't know. Is B in reduced row echelon form? I don't know. Doesn't matter. But this is what I did. Well, when you look at each of these elementary row matrices, okay, elementary row matrices are just making linear combinations of the rows of A. Now that actually, you may have to think about that a little bit. That sure, hopefully each of these, right? If I swap the rows, actually I haven't done anything. Okay, so swapping rows does nothing. Okay, so I haven't even changed the columns. But a scalar multiple is we're just replacing. Okay, so say the first thing we did was a scalar multiple. So suppose I have A is this A1 row matrix, A2 row matrix, down to some AM row matrix. Okay, so these are row matrices. So the scalar multiple times row produces something like A1 R times A2, say, and then down to AM. So I just multiplied row 2 by something, but right, it doesn't matter which one. And so you see here is a new set of vectors. So, I think their proof is not as illustrative as it could be because, see, I get a new set of vectors just when I multiply by that, a row by something. However, this set, the new set, is definitely linear combinations of the original set up here, right? It's all the same vectors except for one, and there I just took R times that vector, so it was 0 times A1 plus R times A2 plus 0 times A3 and 0 times A4 and so forth. And so this new set of vectors is definitely a linear combination of the old set of vectors. But similarly, right, I can get back to A2 by using 1 over R times the new A2 prime, or something like that. And so doing a scalar multiple gets me a new set of vectors. So that was one new way to describe this subspace. And then, if I do it again to another row, oh, that's another new way. So really what's happening, and then similarly, if I truly add, if I add a multiple of one row to another, okay, that is also a linear combination that I can undo with another linear combination. Okay, so, hopefully you can convince yourself that each of these uses of an elementary row matrix just gives me a new set of rows that are the same subspace as before, but we use the transitive property, and they don't really property of equality. They don't really go into that, because I think it's more complicated than they make it out to be here. Because actually what happens is, I start with A, then in what direction? I should have gone En down to E1, but we'll do it this way. Then ENA, that subspace is equal to A, the subspace generated by the rows of A. Oh, yeah, actually, rows of A. I should write it this way. Row of ENA is equal to the row space of A. But then the row space of E1, N minus 1, En A is equal to the row space of En A. Okay, and you just keep going all the way down, and you get row space of E1 all the way to En, Ea, is equal to the row space of E2 all the way to En times A. Right, so, and this is B. And so we get that B is equal to that, the row space of B. So we've got that row space of B from here, but actually we had to kind of do this as an iterative thing, a lot like induction, right? And actually, I probably should use induction to really do a nice job of this, right? To do the ... part. I think it makes sense that I could probably use an induction proof. But at any rate, we get that the row space of B is equal to the row space of A this way. I think to just kind of go, oh, well, E1 to En times A, is B, and they kind of lump all these together. Well, that's a little harder. I mean, I can tell you that each of these things, you know, is either does nothing, as in the case of swapping rows, or they really are just linear combinations of the previous matrix rows that can also be undone the other direction, and so things go both ways to get something like this for any given row operation. But then you see, you really do have to make your way to be one elementary row operation at a time. Now, here's a place where one could do another lemma and do that induction proof and say, well, any number of elementary row operation matrices just in essence is a single linear combination. Oh, okay. If we could show that, right? If I could say that, that whole set of matrices put together, I could have written that as a single matrix that represented a linear combination of the rows of A. Okay, that would be fine, but they didn't do that, and so, I think you have to be a little careful. I think their proof of the theorem kind of leaves a little bit out, and that little bit is that we really have to make our way to be kind of one by one, not all at once. At least not without some other lemma that says we could do that. Okay, so that's our proof, our statement of theorem 3.22 in our proof. And they do make the remark and give an example. I won't go into the example or anything, but they do make a remark. There is no equivalent theorem or equivalent to theorem 3.22 for column space. Okay, in other words, if two matrices are row equivalent, that doesn't tell me that their column spaces are equivalent. It's only their row spaces. So, so that, it's good to realize is that, for column space, 3.22 does not work for that. Okay, we'll call that video done.